All right, well, last section in this chapter, we are going to work on solving equations for x that have radicals in them. And so most of this is going to be review. We're kind of just putting all of our skills together into one section. Number one, so we're just going to dive right in and um, start solving some of these equations. You're probably going to want an extra sheet of paper for this worksheet, especially as we get to the bottom of the page. They're going to get a little bit lengthy, and so just bear that in mind. Don't try to squeeze everything on this worksheet if you're having trouble doing that. All right, so in number one, we know the first thing we have to do when we have a radical, just like a set of parentheses that has an x in it, we need to isolate that radical. So we're going to do that by subtracting 3 from both sides. And we'll get square root of 9. I'm sorry, the square root of x equals 9. And then from here, if we want to undo that square root symbol, we know that we can just raise it to the exponent of 2. All right, so you can always undo any root by raising it to whatever the exponent, raising it to the exponent that matches the index of that radical. So if we do it to that side, though, we also have to do it to this side. And so we find that x in this case equals 81. All right, and number 2, we don't have a radical, but we have that exponent, that fractional exponent with the x. So we're still going to isolate x like we've been doing for several years of math now. And then once we have it in this form, now you could turn this x to the 1/2 into the square root of x, but we don't actually have to do that because the other way to undo an exponent, a fractional exponent, is to raise the fractional exponent to its reciprocal. So if we raise both sides here to the second power, it's the same thing as if we had changed x to the 1/2 into the square root of x. So if we had done it that way and changed it into the square root of x, we would find ourselves in the same situation. We still have to square both sides to get rid of the radical. So if you can remember that you can raise that exponent of 1/2 to the reciprocal of it, which is 2 over 1, then those undo each other as well. So just like the square will the second exponent will undo the square root, the reciprocals will undo each other as well. It'll just save you a little bit of a step. All right, and then number 3. Number 3 is a little bit different because the radical is not isolated. So we have to isolate that radical first by dividing through both sides by 3. So when we do that, we end up with the square root of x plus 2 equals 2. And so now we're going to do the same thing. We're going to get rid of the radical by raising it to the second power. If we do it to the left side, we also have to do it to the right side. And we end up with x of 2. Now, the other thing that is going to be important in this section, particularly, is the second direction here, which says check your solution. And it's always a good idea to check your solutions. I mean, we've had a lot of sections and chapters in the past where they've asked you to solve and check the solution. It's always a good idea in case you made a mistake. In this section, it's actually going to be necessary because what we're going to find out as we get down the page is if you look here at the bottom of the worksheet, it doesn't just say check your solution, it says check for extraneous solutions. So what that means, you can see the word extra and extraneous. It means solutions that are going to appear to work. When we solve for it, we'll get more than one solution, but they don't both make a true statement when you actually go back in and check. So just to review, I just want to use, we're not going to do all 3 of these problems checking solution, but if we want to check our solution for number 1, just a reminder on how we do that. Let me just switch colors here. So to check our solution on number 1, if you remember, we're just going to take what we solved for and got, our 81, and we're going to plug it back into that original equation. And so when we solve for that, we can see that yes, 9 plus 3 does equal 12. So that means that 81 is a solution for this equation. So go ahead and pause the video here and work number 2 and 3, checking your solution. And then after you have that, just turn the video back on and check your work with mine. Okay, so if you worked all those out, you should see that they all gave us true statements in the end. So that means that each of those solutions does work for these problems. There are no extraneous solutions for these 3. Now 10 through 12, we're going to do the exact same way. The reason that they split it up into different sections, I believe, is because we're going to be working with some negative numbers and cubed roots instead of square roots. So it's the same idea, a little bit different on the technique. But let's go ahead and work through number 10. So the first thing we have to do is get that cubed root isolated. So we'll just subtract the 1 from both sides. So now this works exactly the same way as the problems above. It's just that now our index is 3 on the radical. And so we have to raise this to the 3rd power to undo it. All right, so the radical and the exponent you raise it to have to match in order to cancel each other out. So we'll end up with x here, and then a negative 3 raised to the 3rd power. Make sure that that negative sign is in parentheses with that 3, so that you raise all of it to the 3rd power, and then you'd end up with a negative 27. All right, number 11. Same idea here, except now that cubed root of x is not by itself at all. It is not isolated, so we've got to take care of that first. We're going to do that by subtracting the 2 from both sides first. And then after we've done that, we can go through and divide through by 4 on both sides. And then after that, match your exponent to the index on both sides. And you end up with the cubed root of, you'll end up with x equals negative 1/8. And then number 12, that radical is isolated for, so we don't have to do any work here. We do have the binomial under the radical symbol. So the radicand is a binomial. It's going to be a little bit more work after we get out from underneath the radical, but you're going to treat this the same way. So you're going to raise the entire radical to the 3rd power because that matches the index of 3. That will get rid of the radical symbol. And so now, it just looks like this, and so we just have to follow our rules. 118, I believe, and divide through by 2. All right, so same deal here. Go ahead and pause the video and go back through and plug each of these into the original equation to check for the solution and see if you get a true statement back. All right, so all of our solutions check out, which means we don't have any extraneous solutions in this problem. All right, so down here on 19 through 22, we don't have radicals, we have everything in exponent form. So we can follow those same rules. We're going to isolate the x with the exponent if we need to, and then we will use the reciprocal to undo that fractional exponent. All right, so number 19, we have that x raised to the 5/3 power. So in order to undo that 5/3 power, we're going to multiply it by its reciprocal 3/5. All right, we could turn it into the cubed root of 5, sorry, the cubed root of x raised to the fifth power. We could do it that way, but this is just kind of a faster way to do it. But both ways would work, but this is much faster and easier. So if I raise the one side to the 3/5, I've got to raise the other side to the 3/5. So now we end up with 243 to the 3/5 power. Because I'm not using my calculator, I'm going to need to turn that back into a radical so that I can factor 243, and get the fifth root out. So if I factor 240, I think I said 253, I meant 243. If I factor that out with my prime factor tree, I'm going to see that I get 3 5s. Okay, so I'm just showing you the prime factoring under the radical symbol instead of as the actual tree, just to save some space. So I have 5 3s, which means my index is 5. So that means I'm pulling all 5 of those out, but I'm only going to write it one time. So that's showing that I have one group of 5 3s. Make sure I raise that to the third power, and then I'll get my answer of 27. All right, number 20. We need to get that x to the 3 halves by itself first. So we'll just subtract the 3 off both sides. I'm sorry, yes, off both sides, and end up with this. I'm going to raise both sides to the reciprocal. And then these two cancel out. And you are left with 8 to the 2/3 power. Again, I'm not using a calculator, so I'm going to rewrite it as a radical. Cubed root of 8 is 2, raised to the second power is 4. All right, pause the video here and check these two solutions to make sure they're not extraneous, and then start the video back up. All right, so you should have gotten a check on both of those. On number 20, if you did not get a true statement, it could be because you did not raise the -8 to the 5/3. You might have forgotten to follow the order of operations, and you may have multiplied here before you took care of the exponent. So remember, in order of operations, exponents, which includes exponents as well as once you've turned it into a radical notation, it's still treated as an exponent. So it's still the e in PEMDAS. Okay, so you've got to take care of that before you do the multiplication. So if you tried to multiply to a -8 to get -16 and then raise that to the 5/3 power, you may not have gotten the correct answer. So make sure you're following order of operations on all of these. Number 21, we need to divide through by 2. And we'll get this. And then we're going to undo that exponent by multiplying to the 3/5 power. On this side, we'll turn it into radical notation so that we can do it without the calculator. Fifth root of -32 is -2. In parentheses, raise that whole thing to the third power, and you end up with a -8. 22, the exponent is referring to that whole binomial, so it's all one thing. So because of that, we can do the same thing we've been doing. All right, we're going to raise the binomial to the reciprocal. Okay, so what that would look like is I would put it in brackets here and then raise that whole thing to the 4/3 power. Okay, I'm bracketing it just because I've got that x minus 2 in parentheses. So that entire thing in the parentheses is being raised to the 3/4 power. So we're going to raise that whole binomial to the 4/3, and that will undo the exponent. So we end up with x minus 2. 8 to the 4/3 power. And then we'll add that 2 to both sides. I'm going to go ahead and change this into radical notation, as well as adding that 2 to both sides. So the cubed root of 8 we know is 2, raised to the 4th root. That was 16 plus 2 equals 18. So once again, pause the video, check your solutions, make sure there's nothing extraneous, and then you can start the video back up. And once again, you should have gotten check marks for both of those, showing again that these solutions both work. There are no extraneous solutions. All right, so let's move on to the back of the worksheet, and we have number 25. We've got radicals on both sides. So this looks a little daunting initially, but if you realize that, and you remember that we can undo a square root symbol by raising the entire thing to this second power, okay, because the index is 2, we're going to raise this one to the second power. If we do it to one side, we've got to do it to the other side, and that actually works out well for us because it undoes both of the radicals. And then from here, it's just an easy algebra problem. Subtract the x from both sides and add the 7 to both sides, and I'll get an x of 4. All right, so we're going to check again for extraneous solutions, and we see that it does check out. So number 29 may or may not be circled on your worksheet, but we're going to go ahead and do it because probably at this point you're thinking, what is the point of checking for these extraneous solutions? But this one is going to have one, so I want to show you how that works. And as well as this is actually a bit more challenging of a problem. So I want to work through one that's a little more challenging with you. Make sure you have an extra sheet of paper for this one. This one is going to take up a lot of room. We've got radicals on both sides of the equation, which isn't a big deal, except for the fact that it's not going to work out as nicely as number 25. So number 25 worked out really well because both of them were under a square root radical. This one, we've got both of them under the square root, but we have this positive one here that we have to deal with as well. So when this situation happens, and it's not going to be an easy fix for both sides of the equation, you're going to pick one radical. So just pick one radical and isolate it. Okay, so in this case, I'm going to pick that square root of x. It's a little bit easier maybe to deal with initially. Okay, so that will look like this. Okay, so now here's where we need to square both sides. I'm going to square this to get rid of the radical, but I also have to square this, and I have to square the entire side of the equation. So you can see we just made it, by doing that, it's become a little bit more of a challenging problem because we have a binomial over here that we're going to have to use FOIL on. So this side simplified very easily by over here, and I'm going to write it out. 3x, the square root of 3x minus 3 minus 1 times the square root of 3x minus 3 minus 1. So this is not a difference of squares. This is not where you can take the square and square the first term and square the second term. This does not work like that. So you've got to remember that we're squaring the entire thing. So twice, where we need to rewrite it twice. Okay, so from here then, just follow through on your steps for FOIL. So just do the next thing that you know is right to do, which is to multiply those first two terms together. So when we do that, we're going to end up with 3x minus 3. We're multiplying them together twice. So we're going to say 3x minus 3 squared. So you can see that's going to work out really well for us because the square and the index are going to cancel. Okay, so rather than actually multiplying everything out under the radical, I mean, you could write out the square root of 9x um, minus 9, but we're not going to do that because we're just multiplying the two of them together, and we're going to show that square symbol. So there's our first terms. Our outer terms are this, as well as our inner term. Our outer and our inner terms are the same, which happens a lot, when we FOIL, and then our last term. So now let's just clean this up a little bit. This radical is going to go away because the square and the index cancel each other out. We end up with minus 2 of these, 3x minus 3, and then we have this plus 1. Okay, and then from here we can see we can still simplify some. So let's go ahead and take care of all of the simplification we can do. We'll combine those constants and end up with this. Now, you've got to remember what we're doing. We are isolating radicals. So up here, I had you start by picking one radical and isolating it, but now we have to go back in and isolate the other one. Okay, so isolate the second one after you're done with this. So we had to do a lot of work just to isolate that first one and get it all simplified. So now we're going to go back in and we're trying to get this square root of 3x minus 3 by itself. So we're going to have to take everything else to the other side. That's going to make a negative 2x on this side once we subtract the 3x, and a positive 2 on this side once we add the 2 to both sides. And now we can see we almost have it isolated. We need to go through and divide by negative 2 on both sides, which is not as hard as that may sound. Those two are going to cancel, and then we're going to split these two up. So negative 2x minus 2 will give us a positive x. All right, so now our second radical is isolated. So now we'll just follow the rules for getting rid of the radical. Square both sides. Again, we end up with a binomial that we have to FOIL here. So this is x minus 1 times x minus 1. That ends up giving us, when we actually do first, middle, first, outer, inner, and last, we will end up with this right here. Okay, so I kind of short-circuited the foiling. I'm just showing it to you. Foiled and combined. The radical's gone over here. And now we need to solve for x. So we go back to, a long time ago. The way we do that is just get all the like terms together on one side. Wait, hang on. I got ahead of myself here. I combined too much too quickly. So after foiling and combining, you end up with this here. We end up with this once we have pulled our 3x and our negative 3 over to the other side. And now we have an a value that's 1. So we have a trinomial that is quadratic, an a value of 1. That goes back to algebra 2. Algebra 1, we would take the factors of negative 4 that add to negative 5. Write out our two binomials, and now you can see we get x4 and x1. Now, I'm just going to tell you just to short circuit our time here that 4 is going to work. Actually, I'm going to go ahead and show you. So pause the video. These aren't too difficult to try to plug back into the original equation. So pause the video, plug both of these back into the original equation. One of them is not going to work out, and I want you to see that. So here we can see that plugging 4 back in gives us a true statement. 3 equals the square root of 9. But down here we end up with the square root of 1 equals negative 1. So remember, the square root of 0 is 0 itself. And then I take that 1 over to the other side. And that is not true. So that means that the 1 is extraneous. So we want to throw that out, and x equals 4 is our answer. All right, so last is our word problem. And this is a very practical word problem. If you move on to physics, you will use this formula. You'll use a lot of formulas like this. So this is kind of where your algebra skills will meet your science disciplines. Uh, they give you a formula here, and it has to do with the velocity of a free falling object, which is the v here. Okay, they define that for you right there. Um, and that is in meters per second. So velocity is basically speed, but it's different in the fact that it includes the direction. So velocity will tell you not only how fast the object is traveling, but in what direction it is traveling as well. But otherwise, you can kind of think of it as the same thing. Um, the the g is acceleration due to gravity. So that's how they're defining g. That's in meters per second squared. So this is like how fast is something um, speeding up based on the gravity of whatever's pulling it down. In this case, we're going to be talking about three different objects pulling on it. In the first one, you have Earth pulling on it, the gravity of Earth. You've got the moon in the second one pulling on it, and you've got Mars in the last one. And we can see here that Earth has the greatest gravitational pull at 9.81 meters per second squared. So it's a heavier pull on anything falling. The moon has the least amount of gravity, so it's at 1.57 meters per second squared. It's not going to be pulling an object down as quickly. So the other thing we need to know is h is the distance in meters the object has fallen. So what they want us to solve for is they say the value of g depends on which body planet is attracting the object, which is what I just explained. If an object hits the surface with a velocity of 30 meters per second, so when it hits, that is the speed that it was traveling. From what height was it dropped? So they want to know h, and that's going to be based on the velocity it was traveling when it hit, which is going to be consistent for all three of these problems. So 30 is the velocity for all of them. Okay, so we can just go ahead and write that in for all of them. That's how we're going to start the problem. And then we've got the square root of 2gh. That's the other half of this, this problem. H is what we're solving for, so that's the variable we'll leave open. The thing that's changing here for each of them is the gravitational pull. So on Earth, I'm going to set it up for 9.81 meters per second squared. My h will stay open because that's what I'm solving for. Down here on the moon, I'm going to follow that formula, but I'm going to stick in 1.57 for the gravitational pull. And then on Mars, Mars' gravitational pull is in the middle of these two, and so we'll stick that in. So the height that it has to fall from in order to reach that velocity by the time it hits the surface of the object is going to be different. But we're going to solve it all the same way. So if I let's do that. I'm just going to come out here to the side on all these. So 30 is going to equal here in this problem, 2 times 9.81 is 19.62 h. Out here, that 1.57 and 2 will give us 3.14 h. And then lastly, we'll get a 7.44 when we multiply those two together. All right, so now we've got a situation that looks very similar to all the problems we've been doing on this worksheet. We've got a radical that's isolated, so we're going to square both sides to get rid of it. Because remember, the whole idea here now is we're not solving for x, but we're solving for h. So we've got to get it out from under this radical symbol. Okay, so obviously 30 squared is 900 on each of these. And that's going to be, is that equal to what? To the radicand. All right, and now a simple division problem with each of these is going to give us our h. So 900 divided by 19.62 up here will give us a height of 45.87 meters. And you can just round to the nearest hundredth on these. But on the moon, look at the difference here. On the moon, we have to be at a height of, dropped at a height of 286 meters as compared to this 45.87. And that's to account for the fact that the gravitational pull is a lot less on the moon. So if we're going to hit the Earth and hit the moon at the exact same velocity, we have to be dropped or start falling from a height that's a lot greater on the moon to give us time to get to that speed. And then the Mars, we should find a height that's in the middle of the two, and when we divide those out, that's exactly what we find, 120.97 meters if you were falling on Mars.